All right, so this is the first week supplemental exercise. And first thing you should notice in section 1.1, we're talking about inductive and deductive reasoning. Okay, qualified statements, negations of simple statements, and then quantified statements. So we start with some pretty basic stuff. If we look at this sequence, 11, 7, 3, -1, -5. Okay, they're asking me for the next number in this sequence. So if I'm looking at it, it looks like it's going down. I'm going to say this is -9. And my explanation is that we are subtracting 4. Okay, so we're going down by 4, something along those lines to show that we understand this pattern. Okay, how about this? 1/2, 2, 8, 32, 128. It certainly doesn't look like we're adding the same thing each time. The difference between 1/2 and 2 is different than 2 and 8. Okay, but it does, and even here with 1/2 and 2, maybe we can't see what that is, but it looks like from 2 to 8, we're multiplying by 4. 8 times 4 is 32. 32 times 4 is 128. So I think the pattern is multiplying by 4. So then my next number would be 512. If I look at this pattern, 1, 1, 2, 3, 5, 8, 13, this is a fairly popular sequence because it really doesn't have subtracting or multiplication. It's just different. Okay, to go from 1 to 1, I either add 0, but then if I add 0 here, it doesn't work, so it doesn't look like addition or subtraction, and it certainly doesn't look like multiplication is going to work. Okay. But again, this is a fairly popular one. I know that if I add 1 plus 1, I get 2. If I add 2 plus 3, I get 5. If I add 8 plus 13, I'm going to add up to 1. So my pattern looks like we're going to add the last 2 numbers, something like that, or 2 previous numbers. So we can go on and on. 13 and 21 would be 34. So this is what we call inductive reasoning. We're looking at a pattern and we're trying to generalize something. Okay? For each scenario, to state whether this is inductive or deductive. Okay? Remember, inductive reasoning takes me from specific to general, and deductive reasoning takes me from a general statement to a specific conclusion. Okay, so while sitting on the mall, at a bench at the mall, Ruth observes several young males wearing backpacks. Ruth concludes that all young males carrying backpacks while hanging out at the mall. Okay, note that Ruth's reasoning might not be airtight, although she is using some form of reasoning. So what is she doing? She's observing all these kids wearing these backpacks, so she makes a general conclusion that all young males wear backpacks. Okay, this is an example of inductive reasoning. Okay, because we're looking at a pattern and we're drawing a general conclusion. Okay, whereas this is a lot different. All zombies eat brains. Zed is a zombie, therefore Zed must eat brains. Here we're starting out with a general statement. Okay, and we're drawing a specific conclusion. So I'm going from general to specific. This is deduction. Okay. All English majors at the University of Chicago have taken a course in advanced composition. Donica is an English major at the University of Chicago. Therefore, Donica has taken a course in advanced competition. Again, this is a general statement. So we're starting out with a general statement and I'm making a specific conclusion. This is, once again, deduction. Okay? So now we should be able to go to page 2. All right. Again, doing the same thing, trying to conclude deduction or induction. So on Monday, Tuesday, and Wednesday, I'm late for work due to road construction on I-90. I conclude that I-90 is slower due to road construction, so I begin experimenting with different routes. All right, well, again, we're looking at a pattern. On Monday, Tuesday, Wednesday, construction slowed me down. So this is induction, because I'm going from a specific 3 examples and making a general conclusion that I'm late for work due to road construction. Okay? Professor Vasquez has a policy that no one can get an A in her conversational Spanish class if they miss more than 5 days. Due to lack of participation, Jamie misses 7 days of class. Therefore, the highest grade Jamie can get is a B. Again, this is a general statement, a general policy, so this is deduction. Okay? So hopefully that helps a little bit with the induction and deduction part of what we're talking about. All right, then the next thing we're talking about, quantified statements and their negations. Okay, so here we have an inequality. 3x plus 7 is less than 21. Okay, so hopefully we remember some algebra. I get 3x is less than 24, divide by 3. I come up with the solution to this inequality, that x is greater than 8. Okay, so finding 3 examples that satisfy that shouldn't be difficult. I can take a 0, a -2, or even a 6. Those are all less than 8. Okay, now negate this inequality. Okay, so if I want to negate this, all I really have to do is 3x plus 7. I'm going to take the exact opposite of that. That means it's greater than or equal to 31. Okay, not just greater than, because if it's equal to, this is false. So I have to include the equal to here. I don't really have to solve this, because if I want 3 examples that negate this, it's going to be x is greater than or equal to 8. So finding 3 examples would be 8, 10, 1,000. Those are all numbers that are greater than 8 that would negate that. Okay. So number 2, I'm going to leave that one to you guys. Very similar to number 1. Okay. So number 2 you have to do on your own. Okay. Number 3 is a little bit different, so we can talk about this. This says solve the inequality. 5x plus 3 does not equal 11x plus 5. Okay. So if I'm trying to solve this, I'm going to come over here and do a little bit of algebra. So I'm going to subtract 3 from both sides. So 5x does not equal 11x plus 12. Okay. I'm going to subtract 11x from both sides. I get negative 6x cannot equal 12. Divide by negative 6, and I get the inequality. It's an inequality, not an equation. I get the inequality that x equals negative 2. Okay? So give 3 examples that solve that inequality. Any number except negative 2. So 0, 7, 12. Those would all work. Give 1 example that negates that inequality. The only one that would negate that is that x equals negative 2. Okay? All right. So then we get into these quantified statements. Okay? And what we mean by that is we're saying that all A are B. I believe this is section 3.2 in your book. No A are B, or none of the A are B, and some of the A are B. Okay? So we either have all, none, or some. These are all what we refer to as quantified statements. So if I'm saying all A are B, the negation of that is not all A are B, or some A are not B. Okay? Because if I'm saying, let me just skip down here, all of the museums are open today. Okay? That's my statement. The negation could be not all of the museums are open today. I don't want to say none of the museums are open today, because that could possibly both be false. And other forms of that would be some of the museums are not open at least one museum is not open. Some really means the same thing as at least one. Okay? So we can read through here. Okay? And this says, why is it incorrect to say the negation of all of the museums are open is none of the museums are open? Okay? Or all of the museums are closed. Okay? If I say all of the museums are open, that might be false because one museum might be open. So if I say none of the museums are open, that might be false because one of the museums might be open. So I don't want to negate an all with a none. Okay? So for these next ones, none of the museums are open today. Okay, this is a none. To negate a none, we use a some. So I'm going to say some of the museums are not open today. Okay? You could say some of the museums are closed. That's fine. That's what not open means. Okay? But I don't want to negate an all with a none. I absolutely want to use a some. Okay? All right, so let's get a little bit more practice with these. This says some of the museums are open today. To negate a some, I want to use an all or a none. Okay? To negate a some, I want to use an all or none. So I could say this in two ways. I could say all of the museums are not open today, or closed, I guess I could have said. Okay. Or I could have said none of the museums are open. So to negate a some, I want to use an all or a none. Here I have all elephants are wrinkly. So this is an all. So I'm going to negate that with a some. This would say some elephants are not wrinkly. If this statement says all of them are, I just need to find some or at least one elephant that is not wrinkly. Okay? This says no elephants are wrinkly. So to negate that, I don't want to say all elephants are wrinkly because I think we'd both be wrong. So no elephants are wrinkly. I'm going to negate that none or no with a some. I'm going to say some elephants are wrinkly. Okay, so to negate an all or none, we're always going to use a some or at least one. Some elephants are wrinkly. Again, I can use it all or none. I think in this case, it makes more sense to say no elephants are wrinkly. Okay, because if this says some elephants are, it means out there there's at least one elephant that is. Some of these widgets are defective. Okay, so again, this is a some, so I want to use an all or none. Some of these widgets are defective. Let me use an all. I'm going to say all of these widgets. Again, we don't know what a widget is. But what if this says some are defective, all of these widgets, I want to say, are not defective. Okay? So that's pretty good. You should be able to do these last ones. So that's your first assignment in the Math 051, the supplemental stuff. So I've done half of it for you. You need to finish up and do the rest of those and get that to me. All right, good luck. And I'll talk to you soon.